Bismillahirrahmanirrahim. Honorable Chief Guest, Mr. Siddiq Isa Saab, President, Association of Consulting Engineers of Pakistan, Professor Roger Billam, Guest of Honor, Mr. Randolph, Keynote Speaker for the closing session, Professor Lodi, Vice Chancellor, NED, Engineer Sohail Bashir Saab, Chairman, IEP Karachi Center, distinguished authors, presenters, ladies and gentlemen, Assalamu alaikum. We are formally starting the closing session of this two-day conference, International Civil Engineering Conference, ICEC 2019. I'll request Mr. Fawad Masood to recite few verses.
أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم الله لا إله إلا هو الحي القيوم لا تأخذه سنة ولا نوم له ما في السماوات وما في الأرض من ذا الذي يشفع عنده إلا بإذنه يعلم ما بين أيديهم وما خلفهم ولا يحيطون بشيء من علمه إلا بما شاء وسع كرسيه السماوات والأرض ولا يؤوده حفظهما وهو العلي العظيم صدق الله العظيم.
Jazakallah. Ladies and gentlemen, all of you are now requested to please rise for the national anthem. Before I invite the keynote speaker for the closing session, just for the information of the audience that the 2 days of the conference and including today's closing session is being live streamed on official website of the IEP, that is IEP Karachi.org.pk. Today we have with us the renowned conservationist Mr. Randolph Langbeck. He is international consultant in building conservation. He'll be talking about a talk which is in series of the previous talk that he gave the other day at the first South Asia Conference on Earthquake Engineering. The title is Recovering the Lost Moment, How Timber-Laced Masonry May Hold the Secret to Stopping Pancake Collapse of Concrete Moment Frames. So he'll be mostly focusing on part 2 of that talk, where he'll be talking about the brick masonry and comparison of brick masonry with the framed construction. So ladies and gentlemen, I would like to now invite Mr. Randolph.
Thank you. Thank you, Sangi, Professor Sangi. It is such an honor, and I also have to recognize Mohammed Masood Rafi for inviting me to the first South Asian Conference on Earthquake Engineering, but also inviting me to speak here 5 years ago, it was, which was done by remote by sending a movie. How many heard my speech then? Only one? Two? no one else is here. Is there? Saw the meeting. That was 3 in the morning. I got up to do the Q&A because that was done by live. But I managed to. The movie was made as a part of my speech at the Institution of Structural Engineers in London. So I had then talked. Was this working? Yeah. Talked. It's only 6 months earlier in London, and they gave the opportunity to single out a section of it as a movie for being able to share with you. But now I have the pleasure of meeting you all, and it's been quite a wonderful experience. This is only my third trip to Pakistan, first being after the Kashmir earthquake. And for that, I have to thank the SDC, the Swiss Agency for Development Cooperation, and UN Habitat for hosting me in Kashmir and to be able to take me to some of the places you'll see. And then again for UNESCO after the Indus Valley floods. So with that, I'll move on. And the picture I show here is just an introduction. My early work that brought me into the field of earthquake engineering and masonry and historical construction was spending the 20 years of my life, beginning when I was a college student, documenting as a journalist, writing about the textile mills for some reason it went out of focus. Is there a way to fix this? In New England, Manchester, New Hampshire, named after Manchester, England, and then I also did this in Great Britain, the landscapes of the Industrial Revolution. But these buildings were 6, 7, 8 stories high with running machines in them. The looms are a ricochet machine, and they vibrated it at the same intensity, really, pretty much as an earthquake, but for 120 years of their existence. And they shared a seismic system that was invented in the early 19th century that's the same as what now is required for the retrofit of masonry buildings in California. It was reinvented effectively for that. It's out of focus. If I could have some help and bring it back into focus. This was followed by my having a fellowship to India, where I discovered Kashmir. It's a little better now. It's a little better now. Okay. And I discovered Kashmir then, which was like a lost medieval city, but it had a timber-laced construction. There it is. That proved to be earthquake resistant, as documented in the 1880s by British visitors who experienced and documented the effects of the earthquake that happened in the 1880s. This is before I got involved with earthquakes of the present day. But I studied that first in 1981, in the year that I spent in India. But I'm switching the story now to the late 19th century in Chicago. What is considered the first skyscraper is this building here, only 10 stories high, but as what was then a mixture of iron and steel frame, but a completely coherent, effectively moment frame structure, but with the masonry around and infilling the walls. It was the first phase of tall buildings, and here this picture was taken only 3 days ago here in Karachi. These are 10-story buildings. So, and we don't think anything of it. And as we drove by, I said, "Are you really serious about these buildings? They look like they all have are vulnerable to soft story collapse. And everybody I've talked to of one of the colleagues here says, yeah, they are. So I guess there's a bit of a problem. But back to Chicago, this was a new world because buildings till then had masonry, solid wall structural systems. And it was a totally different experience to be an engineer in the days of Christopher Wren or even Michelangelo or Brunelleschi, who were working with masonry. It is a lost art to a large extent for all of us architects and trained and the engineering that comes with my architecture degree, but I'm not a structural engineer. But now I am very much embedded in the effort to do engineering of buildings, and that's what I'll be speaking to. But the switch to frames is there some, hopefully it'll communicate. And as you see, what was remarkable is the complete steel frame. This is now the transition from iron to steel. One of the best iron frames buildings I found was in India, in Mumbai, what was then Bombay. But here, steel frame. And the Bessemer converter process brought steel into massive production, and it became the basis for doing structure. And you see the windows are ever so much larger than when it was a bearing wall building. And one very good example of this and the engineering of it is to look at the Flatiron Building in New York, because there's these pictures of it show that the putting of this heavy wall masonry on it is by starting the building of it upper as well as at the lower, not that's to avoid it bearing on itself to become a bearing wall, because it's hanging off of the frame. So the wall is the same thickness from the basement to the roof. And that's a transition in the building construction. But remember, now we're talking about a huge amount of masonry, multiple leaves of masonry in a frame building. And so how do we do this? And there is a textbook authored by a gentleman by the name of Joseph Kendall Freitag, structural engineer, who did a textbook on how to do tall buildings in that era. This is published in 1900 and again in 1905, a second edition. And he says, still no definite or even approximate values can be given to the infill masonry except their purely static resistance or weight. But notice that he's saying it's essential to the design. More or less like the rest of our body from the bones, the holding the body, the anthropomorphic analogy for the making of buildings in that period that are structural frames. And here's a good example constructed in San Francisco after the city burned down in 1906, which I'll get to in a moment, with this system. And you see how much masonry there is here. And that the steel frame is not a braced steel frame, but it has little, if anything, little haunches here. But imagine the weight of the building. So we're talking about a different kind of building than we're used to today, where the whole effort is to have as little masonry as possible and to have the frame is designed and computed and mathematized with portal frame analysis. But you see how lightweight the frame is. The last of this series of buildings is the Empire State Building, 100 stories. And it's heavy wall masonry. They even did some testing with some measurement instruments, and in a very heavy hurricane windstorm, they computed that not until they saw a crack in the masonry did they even come a load onto the steel frame. So looking at San Francisco before the earthquake in 1906, it was already full of these buildings. It was the biggest city west of the Mississippi in North America, and economically the center of the whole left coast of the continent. And then the earthquake came. The earthquake, of course, then initiated a fire which burned through the entire downtown of the city, burning out every single building, including all of the fireproof buildings that were steel framed with masonry infilling all of the contents, just like with the World Trade Center after the attacks, burnt. But instead of like the World Trade Center, the buildings remained standing. And you see the fire went everywhere. The firefighting in those days was primitive at best, and it broke all of the earthquake had already broken all of the water lines. So it was impossible. It was only until the winds changed to blow in from the west that the fire stopped. That's why we have Victorian wooden houses still in San Francisco today. But you see, this is after the earthquake, before the fire, and look at how the fire took the rest of the city, is what took the city down. But still standing here under construction are steel frame buildings, but there are many that were already finished and occupied. And believe it or not, 110 years later, those buildings are still there today. And not only that, they had to be thoroughly renovated because they all had fires burning through them. And one of the top structural engineers in earthquake engineering in California said this in a paper on the 100th anniversary of that earthquake, and saying that the question of if you evaluate these according to our current systems of evaluation, the masonry is not included as a lateral force resisting material. It's only dead weight, just as Mr. Freitag had anticipated before, but he had considered the masonry essential, but then through the rest of our last century into the present, the masonry has been not included as part of the structural engineering, and that's what I want to get to later. But to see the effect of having the fire as well as the earthquake, why this is not functioning there, it's coming now. The flood building is one very good example. This had an internal steel frame. As you can see, it's a heavy wall and architecturally very sophisticated masonry building. Again, the Fairmont Hotel, after the fire, is exactly the hotel that you can stay in today when you come to San Francisco. And here's the lobby after the fire, and then the lobby today, like this. So, and I show this to show what we're dealing with, because that's the building as it is today. And I'm here not going to speak so much of the World Trade Center, but there's one building that was totally burnt out from the spray of the fire when the buildings collapsed from the burning of the fire, heating up the steel until the point where it failed. One building that burnt out was called 90 West Street. It was built in 1908, designed by a famous American architect, Cass Gilbert. 28 stories made it almost, at that time, I think it was for a moment, the tallest building in the world. It was still there until the collapse of the towers. And today it's the only building that is still there that was burnt out from the collapse of the towers. And in fact, it was very interesting to see that the columns were beginning to compress from the expansion from the heat. And you then have to ask the question, well, why didn't this building collapse? It was most interesting because to compare that to the 1906 fires in San Francisco, you see the same thing happen. So I finally figured out from seeing it witnessing it live by going through that building, why these buildings didn't collapse. And why do you think they didn't collapse? When they were compressed, the columns are compressed like this. Why wasn't it a long column failure or something like that? Or why didn't this just continue to collapse? The reason that I think of is that the masonry had kept all of the exterior bay of the frame cool because it was heavy masonry. That meant that the fire burning inside, where all of the fireproofing had fallen off because of the earthquake, the pressure on the columns went up and up and up until it crushed the column. And then as the outside frames were cool, the building didn't collapse. And they came back and repaired the buildings. Those pictures are in buildings that are still there today. They replaced the columns. So it's a remarkable essay in the resilience of a building system that was invented at that time. And then you have to ask, well, why do we have every single one of these buildings of frame construction, steel frame construction, remain standing in repairable condition after the worst earthquake in North America, outside of one that was in Alaska. And then these are falling down like 10 pins in Turkey, in this one example, but in other places too. And here's a picture I shot in Kabul, Afghanistan, but of showing a frame, and it doesn't seem that badly built, but I just show it because this is frame construction as well. So why are we having a problem if the buildings in San Francisco survive that problem? And here is where we get into the moment frame issue. Of course, that's predicated on the bending of the beams and columns in a sympathetic way up through the whole height of the building. But think of it for a minute when we have masonry in them, and I'll get to that, because there was a change in the mathematization, in the portal frame analysis from the time that the earliest of these buildings were built, from a pin connected because of the problem of the indefinite structural analysis where you don't have a methodology for having simple three equations of equilibrium. So they changed this just doesn't seem to be working. Is there? No, the receiver is right there. Right there, I'm pointing straight at it. It was working earlier. And so the contraflexure method, but think of it for a moment. This then meant that you could do much more precise calculations. It reduced the overbuilding. Beams got smaller because now you had more precise calculations for their sizes. So that's just one thing. But remember, all along here, I don't know what to do, but you have another one? It just is very slow. That in addition to that, the development of reinforced concrete as a frame system, in my estimation, is a material and system very much different than wide flange steel. And when you look at it, the whole idea that the lateral resisting system that you're calculating is the beam column intersection. It's no longer, unless you build a shear wall building, no longer any more than that. And so we have this problem. And then I was talking with Edmund Booth in London, by email, about, and he says it's sometimes 5 to 11 times the forces, shear forces in the beam column section of the beam than anywhere in the rest of the beam. that for concrete, the compressive resistance of concrete is often very much less than the tensile strength of the steel. And then when it gives way, there's nothing. Then it goes to collapse. So you compare that with, in this instance, in the Mexico City earthquake of '85, a steel frame building that had very little lateral in it, and the masonry was quite small, as you see in those central windows. It bent, but didn't collapse. So we'll get into that because we see in Turkey, and we see even some examples in the Kashmir earthquake here in Pakistan, the collapses were profoundly extensive. And very often it's because the masonry in the upper floors that the buildings have all of the lateral now, the forces are greatest at the base, and if there are walls there, it takes them out, such that there's a collapse mechanism. So these infill walls, and I would remember I was talking about the masonry in the San Francisco earthquake, is infill as well as cladding. But here we have infill walls, but they're not part of the engineering, and but they are part of the building. And as we see, that perhaps you could even say for 100 years that the engineering calculations that we've been using for these buildings is incorrect to a very large extent. And even if you do a study of the diagonal strut effect of the masonry, but if the masonry then collapses out of the frame, then you all of a sudden have no resistance in one area. And so you have the potential for catastrophic collapse because the masonry infilling, as you see here, has jacked this column, and this building was minutes from collapse because here is all the rebar wound up from part of this intersection, but for some reason it didn't go all the way down. Perhaps a little bit of resistance from interior walls, it remained standing. This is 1985 earthquake in Mexico City. I'll give you a little bit, and unfortunately the picture is a bad copy. But again, in Goljuk in Turkey, in the Izmit 99 earthquake, this kind of damage, the building had walls that went to the ground. But the lightweight infill now is insufficient. And so you have a collapse mechanism if it breaks up some of the walls near the base of the structure, and all of a sudden it's just like having a soft story. But this one I want to show you in Gujarat earthquake in 2001 in India. These buildings were meant to be identical. They finished this one and it was occupied. They then started building this one, and the earthquake came when it was at that point. Frame action could occur here. That's the basis on which all the calculations are produced, is the frame action of a bare frame. But not anymore when you're living in it. Then the infill walls are there. They're not part of the calculation. They're not even enough over-designed to keep it from collapsing. So I show this in Turkey. We photographed these after the '99 earthquake. This was under construction when the earthquake happened. And I'll never forget stopping to take a picture, and I thought that I was photographing a military site because this guy came out, climbed over a barbed wire fence, and came up and asked me what I'm doing. I was just simply photographing what turned out to be his building. Well, I came back, of course, a number of times after that earthquake, and he had demolished a couple of stories at the top. Well, do the arithmetic on that one. He obviously, having the picture published around the world by not just me, but every engineer and architect who came by after the earthquake must have stopped and photographed because it was right by the toll booth. And the building is still extant, but when you look at it down at the bottom, the thing that, instead of knocking down extra floors, the thing they should have been busy building is a shear wall. Excuse me. You know, it looks like an accident just waiting for a moment to happen. Of course, they believe that Istanbul is next on the list for the earthquake that's on the Marmara Fault, the Anatolia Fault. And, but then when I came back later, all that they could give me for the earthquake hazard mitigation was a whistle. This was handed out. This is if I get stuck in a collapsing building and have the presence of mind not to crawl under the couch, but lay down next to it, I might be able to be heard by the rescue. A whistle. The World Bank said there are too many buildings that need a seismic upgrade for them possibly to be able to provide the funding for it. So the only ones they were able to fund were hospitals and fire stations. Well, I rest my case now here in Karachi. This was taken only 3 days ago out of the walls of the car when we were going to the previous earthquake conference. And that's the kind of concrete building that we're dealing with. And many, many countries, it doesn't matter where you are. And the US would have these buildings too, except we build most of our buildings that people live in out of timber. And so there is, I'm going to show about the '89 earthquake, which in some ways has some recognition or memory from the previous earthquake. But what's interesting is the kinds of buildings that I'm talking about from the 1906 earthquake exist in Oakland, California, in the '89 earthquake. And it was amazing how much of a fight we had in order to keep buildings of this quality and this quality from being torn down because of the level of damage was that. And that level of damage was considered a loss of strength, even though that's good performance as far as a building is concerned, because the masonry is the stiffest element. It means that the frame underneath has not changed in any way. And so a lot of these buildings, they've stripped off the entire interior withe or leaf of masonry and putting reinforced concrete gunite to strengthen them. And one interesting example is the Hotel Oakland, which was turned into senior housing. And they had ripped out all of the interior masonry walls that were infill walls when they did this as a seismic retrofit. They added a shear wall that was too narrow. It moved in flexure. And look at all of the exterior masonry damage. It was the only building that had that much exterior masonry damage, and yet it was the only one that had been retrofitted. Wait a minute. What's going on here? It is the result of taking out all of the interior infill walls, which were thin walls of brick, but nonetheless they contribute to the stiffness and the resilience of the building. This is a replaced, as I show here, that entire wall. Another example of a building of the earlier era with masonry exterior, they felt they needed to put in shear walls. It ended up looking like that. In the most expensive retrofit, probably 4 times the cost of actually replacing the building was to do base isolation on the 1920s era City Hall, which was a steel frame building that you see here that had simply developed some cracks in its masonry interior and exterior finishes. And you can then see the steel frame. And here they then put base isolation. And you see it exposes what was actually a very robust riveted steel frame in the building that is then completely jacketed and surrounded by the masonry. and that's where one of the base isolators is going. Well, you know, I, together with an engineer as a consultant, were hired by the owners of this building because they needed a repair that would be approved by the city. And what was interesting is I found an engineer in Los Angeles who was willing to, and had a method of analyzing the strength of the building, including the resistance of the masonry. And at the end of the day, we did the retrofit for this much cost compared to the retrofit of the city hall at that much cost by comparison. It's the only one that was done like this because it didn't get shut down as many of the other buildings did because the cracks appeared in what appeared to everybody who studied it a back wing, but in fact it was structurally part of the building. I have a proposal that, and those of you who saw my lecture in the other conference will understand where I'm coming from with the traditional construction of Kashmir in India and Pakistan. But looking at that combination in Turkey, this is called himush, and in Pakistan it's called daji dwari. But here is a perfect example of this problem of the performance of reinforced concrete. And it doesn't mean that reinforced concrete can't be earthquake resistant. I want to make sure I leave you not saying that all of your work in concrete is defective. But most of the buildings built are not even engineered. They're often built just following a rule book and a contractor putting them up. But nevertheless, what you can see here is the performance of the himush building on top of what was a bearing wall masonry base is so resilient. It's not strong. We're talking about a resilience of weak structural systems. But how can we get some of that performance into reinforced concrete is the question I asked after I have now studied this traditional system. Here is an example in Indian Kashmir in Srinagar of a multi-story building. And you see it's 4 stories high of daji dwari construction. So this kind of construction, which is only 1 brick thick, we're talking about thin-walled frame structures. But why is this different performing than concrete buildings that have rebar and all of that with infill walls? So if you look at, for example, the collapsed infill walls of one of these concrete buildings in Turkey and compare it to a building right next door of the himush style, you realize, wait a minute, this wall worked using the engineering meaning of the term worked. So the plaster having fallen off means that it's working back and forth without a collapse of its infill panels. The masonry is working together with the timber frame in a way which, if you see the walls in the concrete buildings, they just develop diagonal tension cracks, which in Italy and Portugal are called crosses of San Andrea, the saint who was crucified on an X cross. The idea I have is to have what's called a subframe. So I call this armature cross walls because these are not to be confused with shear walls. And the reason is that a shear wall is like designed to be like a deep beam and have a foundation and have flanges and all of that in order to meet any kind of code that's been developed for them. But a cross wall is a term of art that came from the building code they developed for existing buildings, the Uniform Code for Building Conservation, UCBC, and they call cross walls just the interior walls of a brick building that is being retrofitted. You can take a minimum factor for them to compute into your calculations for earthquake resistance. But by having a subframe, which in a multi-story building could look like this, there are even ways that I imagine that one can introduce this kind of framework into an already extant wall without having to demolish the wall, which means the building can be improved and retrofitted without essentially replacing it. And this particular power plant that has a system of lightweight steel and is essentially otherwise a masonry bearing wall structure that's held together was right across the street from that. A reinforced concrete frame building that was under construction at the time that the earthquake collapsed it, even though it hadn't been fully infilled yet. So, and then we go to El Salvador and the earlier San Salvador earthquake of 1986. And I looked at this building and I thought, well, you know, I could see that it had a soft story collapse, and finding the cause of that was not interesting. It's why the other stories didn't collapse too when you drop the whole thing from the height of 12 to 15 feet, bang, on the ground. That's even worse than the initial seismic event. Why did the building remain standing? And I got upstairs, I climbed in through a window, came upstairs and saw that there was a subdivision of the infill walls. The infill walls could remain in place. And then in addition to that, I think that the walls were thicker as well, and they were solid bricks, unlike the Tula blocks that you find in Turkish construction. Iran, most of the building construction there is lightweight steel, interestingly enough. You'd think, we got better performance from that. Well, it didn't turn out to be the case. In the BAM earthquake, there were the steel buildings, almost all of them in the center of the city collapsed. I think they forgot to teach the builders how to weld, because it was almost all from welding failures. But I looked at this and I thought, you know, what's going on here? Why is that there? Then I saw this in a building that was under construction, and I saw that again in a building where they hadn't finished the outside wall. And that is the front of a building where the back didn't have windows, and the back fell out, but the front remained standing. I thought, here's a good example of a subdivision of masonry with very lightweight steel, almost like storefront rolling door steel, which is accessible in almost every place. And it made the masonry preserve the building from collapse. The masonry did the lateral resistance. And I show this because the inspectors, many of whom I don't think were really trained engineers, who went around after a smaller earthquake that was a year after the big earthquake in Istanbul, in Marmara and Izmit, and they told the occupants in these buildings that suffered damage in what was the Orta earthquake, that these buildings are essentially ruined, don't you think? We'll give you new buildings, and we'll take them away from what might be a landslide area, maybe a little bit here, it could landslide in the future. And they built a whole new village here, and the old village is right there. And then I went to look at the new village, and first of all, they didn't have any barns for the animals, they didn't have any mosques, they didn't have any store. But wait a minute, one of the buildings hadn't been stuccoed yet. So the new buildings are unreinforced hollow clay tile with a solid, stiff concrete roof, and that's supposed to be better? I'm sorry. The beauty is those old buildings actually were in a resilient style that I'm now proposing, and I'm looking for people and partners to really research the idea of the armature cross walls. I'm taught its effectiveness by those buildings that had that system. And I just want to leave you with one thing, because in improving the Dudgy style after the Kashmir earthquake. The system that is essentially demonstrated and approved has these diagonals in them. And the traditional system has timbers that are diagonal, but they don't brace. They don't become braces. And they're small and thin and casually put together here, and the masonry is what's going to carry some of the load. But I have a feeling that some of this came in because there's a conventional wisdom within engineering community that you need that in order to make sure it's braced. And that so almost all of the studies have been done in here in Peshawar on their shake table or push test. You see, but the first thing that happens is it comes apart at the corners. And then there was an engineer at Arup in London of Turkish extraction. His parents were Turkish, Kubilay Yilmaz, who did a very sophisticated finite element analysis of this, what he considered to be the example of Humush-style construction. And every time he ran the model on this Cray computer, it took a week to run it, the video that would come out would show the building just simply bursting and falling apart. And I was consulting with him essentially, in a kind of partnership. And I said, take the diagonals out. Well, he said, I can't take the diagonals out. It would require a whole nother $100,000 or euro or pound cost to do it. But he shortened them, and you see the effect of each making them shorter, shorter, shorter to the most. Finally, when he made them short, the shortest he could make them, you got a hysteresis loop that is effective. That shows a level of energy dissipation that I have always ascribed to this system from empirical analysis of my own examination and being and studying it over time. And the effect of it can be seen in that because the effect before was to burst the frame. And so it then was able to rock back and forth. So when thinking of it, can you give him a bump? He's totally asleep. Yeah. I'd say when you work on this system, leave out diagonals, because if you look at the system in Srinagar, Kashmir, they have only diagonals from erecting the time they erected the building, but most of the panels are rectangular. And of course, the masonry gets so much better if you do that, because you can put in the blocks, so you don't have to cut them and make them fit into a triangular space. But I felt that this whole question of diagonals was brought to my attention just a year and a half ago in the earthquake that most recently happened in Mexico City on the same date as the one that happened, a date in the year, as the one that happened in 1985, which embarrassingly enough is my birthday. But the one building that I got involved with through one of the apartments owned by somebody we knew, I discovered that, in fact, they had put in diagonals. I think they had put them in after the 1985 earthquake, as they had in a number of other buildings. And you see the damage, the damage around the infill panel that was even damaging the essential concrete frame of the building. And this is the building here. Whereas the inside walls were framed with orthogonal panel subdivisions of the infill, which, as you see, the kind of rupturing you see here is more towards the center of the panel. It's not disturbing the frame, the structural frame of the building. Well, what's interesting is this building may be torn down and replaced. Had they not done this, the building wouldn't have been damaged so much. So there was a kind of a default to brace this in a very stiff way. And what I found very interesting that I only just recently discovered in my research, after the 1906 earthquake, all of the engineers at that period really studied this earthquake in great detail. And the analysis, one of the analysis documents said that I wish this worked. In the writer's judgment here, the diagonal framing is not desirable. This is after 1906 earthquake. They're saying avoid diagonal framing. This is now 110 years ago. For frame construction, they're saying that in their judgment, it's not desirable for high buildings. If the stiff frame of triangles is subject to earthquake vibration of severity, rupture at the weakest places is extremely likely. Very interesting to find that back then, when in fact that problem continues to this day. And there's a tendency to look at a frame and say, wouldn't it be better if it were like a truss? It's counterintuitive, I think, to think that it would be worse. And yet, I want to leave you with this concept, and it's a style of construction that dates all the way back to ancient Rome. And notice that in ancient Rome, the only diagonals you see here are on the fence, but the actual subdivision of the wall for what was their version of dudgy or half-timber construction is square panels or rectangular panels. So I want to, in my closure, take you to Haiti for just one series of pictures, not much, but as you know, the National Palace, if I can get it to, there it goes, collapsed. And the National Cathedral collapsed. Both of these were concrete buildings, and that was the status of the rebar I found in many of the buildings, rusting away. They're 100 years old. The National Palace, in fact, was built by the American U.S. Navy, so you'd think that a part of it was. You'd think that it would be good construction. Well, but a 100-year-old concrete building is reaching the end of its useful life. And so we have an example here of a school building that was of, indeterminate construction. But I wanted you to show you the church, because that's pancaked. But the church, wait a minute, what's happening here? This was built in 1900. What's going on? Is it masonry? Turns out it was cast concrete blocks of masonry. And held together with steel, thin steel framework. It was built 20 years before the National Cathedral, and it went through the earthquake with so little damage. And here's a brick masonry building in the churchyard of the same kind of construction. And the steel members were brought over from France. Same kind of construction as the church you see here. It never failed to have a Sunday church service. It's not been repaired. It's exactly as it was after the earthquake. And so you have to say, wait a minute, maybe this is a view not into the past only, but into the future. And if you look at it on the outside here, it's a framework of having, almost like what you now have is reinforced concrete, but putting the steel on the outside as tying it together as a framework where you can see it, maintain it, repaint it. It's exactly as it was. It's 110 years old. It was built I think in 1890, 1900. And perhaps that's a view into the future for what could be a different form of reinforced concrete. A reinforced concrete that could last. And I then wanted to just leave you with a picture that some of you saw in when they watched my movie in the previous conference. Because when you look at this, I came to the same view that Piranesi, a quarter of a millennium ago, did his drawing, his engraving. I photographed it and constructed my photographs into the same view. You're looking at unreinforced concrete of that roof, having sat there for 2,000 years, unmaintained for 1,800 of those 2,000 years, and then over the last quarter of a millennium, not changing that much in dimension between the two documents, as a demonstration of what is a remarkable material. Thank you very much. And those of you who want to see the movie about Rome, I show you the website where you can download it, play it. It's a 45-minute movie, and there'll be a book coming out in 2 months on the same subject. But shall we take some questions?
A couple of questions. We have time for a couple
that'd
of
be
questions.
great. Yeah, I'd love to. And feel free to make comments or disagree with me or whatever. This is a dialogue, and I wish to open it up because I'd like to see some people be able to take this to. Thank you very much.
Very good lecture.
Thank you. I'm giving the.
You are comparing it with the collapse of the multi-story building, pancake strike, which
Yes.
is really very common with flat plate construction.
With what?
With flat plate construction, artistic flat slab.
Flat slab construction.
That's without beams.
Yeah,
right?
okay.
So that's very common.
Yeah.
And all the world had their failure. America, Europe, everywhere. And then they said it is due to punching shear. But your lecture is about the lateral loads due to earthquake.
Yeah, I would.
How would you compare this? How would you compare this falling down slabs like that?
Well, I obviously haven't taken it to the detail of what the failures were in each of these buildings where you have pancake collapses, or I guess in this part of the world and in India, we would call them chapati collapses. But the problem is not unlike that of the World Trade Center, which was a steel frame building, because once there is the onset of a possible collapse, in that case it was the superheating of the steel outside perimeter frame, because there were no columns except for the central core, which actually remained standing until the whole outside was collapsed. The carrying of a whole building to the ground is usually from a major failure in one area. The punching shear is, of course, a function of a failure to have what is the equivalent of moment frame behavior, meaning that the sinusoidal reshaping of the members that allows the building to be distorted and then come back. I mean, that there's a certain amount of elastic limit. But the moment you put in stiff masonry walls of either system, all of a sudden you're taking 100% of the forces until there's a failure. I mean, and the way of thinking here, and particularly I think it goes together with concrete more than steel, because I showed a failed steel column, but the problem with concrete is that so often the rebars are more effective in the tensile direction, such that the first thing that happens is the concrete is crushed. Then there's no recovery. That's what I mean. And I showed in my previous lecture this picture of the minaret still standing, and after, with all the concrete buildings around collapsed, and the unreinforced masonry mosque was still standing. And then I showed a modern mosque where the minaret was fallen. And I talked just simply about that, about the fact that the steel reinforcement jacked it such that the structure can't recover.
Thank you.
Okay, yes.
Thank you. One quick question.
What? Yes, right there.
Do we understand that you are saying that if you make a structure too stiff, it's better to have a structure which is able to deflect so that the loads are not concentrated at the corners?
Yes, well, I am. And the whole idea, I think, that I have with the armature cross walls is to take advantage of the fact that the walls will stay with the building as it is forced to move. And they do so by going inelastic from the very beginning. In other words, you have a very initially stiff but weak wall. In other words, all of the edges, you have now a small panel where you have masonry. And one of the things I didn't mention, what's really essentially a part of my idea, is that the mortar must be weaker than the bricks. And whenever you do an infill wall of any type, make sure the mortar is weaker than the bricks. Stay away from cement mortar. Do lime mortar. Try to get all of your concrete companies, if they do business in selling cement, make sure they all also market, quicklime. And you make lime putty, and you make lime mortar, which is a much better performing masonry mortar than cement mortar is. And it's not brittle. And you want to make sure that any kind of movement then, that even then as the masonry panel is distorted, is along the bedding lines of the bricks rather than a diagonal tension crack that cracks the bricks. And because that's a non-recovery situation. The same way I talk about concrete is brittle. Concrete is brittle. So you don't have inelastic behavior in concrete the way you might within steel. And you're not gaining the benefit of a steel frame having it in both compression and tension. You only have the steel in tension. And the failure of concrete, you're using for basic, if you're using the American code, you're designing it as a linear elastic design problem for plastic behavior, because a design level earthquake, you have R factors that actually reduce the forces, and it's expected to be damaged. So expecting the building to be damaged in your design, and obviously you want the damage not to lead to collapse, but in a concrete building, that initial inelastic behavior is by definition the crushing and the breaking of concrete. You just want to make sure it's not collapsing. But it's damage, which then requires the replacement of the element in a repair. So it's worth thinking about these walls, because I see these walls as kind of an initial sacrificial element where you have tremendous amount of energy dissipating damping as it's moving and breaking the material, but it's not falling out of the frame. It's able to go back and forth, and that way the breaking of the beam column intersection, which occurs a little bit later from when the frame goes inelastic, you still have the behavior of the wall supplementing it.
All right.
That's the
Thank you.
concept.
Okay,
Thank you very
Randy.
much.
Thank you very much. Please have a seat. Thank you. Okay, now I would like to invite Professor Roger Bellham to come up and please say a few words.
So thank you for inviting me here. As you know, I'm a geologist or a seismologist, so I feel very out of place, although I'm considerably impressed by the talks that have been given at these various conferences this week. I've been asked to say something. I only have one thing to say, and that is that the input to all your design considerations, of course, is the acceleration from earthquakes, the horizontal and vertical accelerations that you expect in the future. One important aspect of this is that you have to listen to geologists. You have some very good geologists and geophysicists in Karachi, in Pakistan. But they need to be encouraged to go out and look for the missing data that is important to constructing hazard maps. For example, you have a nuclear power station and another one going ahead on the coast here. And the criteria on which the design for those power plants is based is, of course, dependent on the accelerations you expect. But the history of earthquakes in Karachi goes back 200 years. 200 years is like the blink of an eye in geological time. It is quite possible that an earthquake with magnitude 7 could occur within 50 kilometers of you. It is almost certain that an earthquake with magnitude 8 will occur within 100 kilometers of you in your future. This has never been experienced by anyone alive in Karachi or anyone who's lived in Karachi or knows the history of Karachi. I've only to remind you that Karachi was a fishing village with 200 people in 1800. And prior to that, who knows how many earthquakes will have visited that village? Who knows how many tsunamis? I would like to encourage the young people in this audience to go out and look for the evidence for those earthquakes. They are going to be left in the form of tsunami deposits inland. They're going to be left in the form of previous slip on mapped faults. They're going to be there in the seismic sections from your explorations for gas and oil. These data need to be collected together, and it hasn't been done yet. And I expect you guys, you young guys, to go out and do it. It needs doing, and it's so important for the engineers in this room. So thank you for inviting me to your conferences, and I hope to be back again with answers to some of these questions.
Thank you very much, sir. Now I would request Professor Sarosh Lodhi to kindly come up on stage and say a few words.
Bismillahirrahmanirrahim, respected guests and delegates for the conference, with Randolph and Roger, I have nothing much to add. So I will be very brief and quick. And when Randolph was showing some of the pictures of Karachi, which was taken during the last couple of days, that reminded me of a very famous word that Roger said once. And he said, Sarosh, these are not buildings. These are the weapons of mass destruction. So indeed they are. Our engineering community needs to learn a great deal about those things. We have fiddled in the past with the stiffness calculations of the infills, especially the kind of concrete bricks, the concrete blocks that we make in Karachi. And we've tried, because that adds a lot of stiffness to the structure and alters the fundamental period of vibration. But at the same time, they're extremely brittle. So they're there for one moment and then they're gone next moment. So obviously putting in structural interventions are important. We need to look at and explore some of the other things as mentioned in the keynote. However, I personally feel, I think the things went wrong when we gave away the curved construction from arches to domes and moved on to flat constructions, beams and slabs and columns, and this is where the problem started. If I wish we could still go back to those curved structures, we would still be saving a lot of lives. Anyway, I mean, I don't really want to convert this thing into engineering. I would, however, say just one thing. I wish Roger can come back and stay here in Karachi for a year and guide us through to develop a plan to be more resilient Karachi. Thank you very much.
Thank you very much, sir. Now, I would invite Dr. Shamsoon Fareed, who will be sharing some conference highlights with us. Dr. Shamsoon Fareed.
Respected Chief Guest, Siddiq Isa Sahab, Guest of Honor, Professor Roger Ballum, Honorable Vice Chancellor, NED University, Professor Sharoz Ashmat Lodi, Engineer Sohail Bashir Sahab, respected faculty members and students, Assalamu Alaikum. Indeed, it's my proud privilege to be a part of this organizing committee, in which at the initial phase, 42 technical papers were submitted for peer review process. After initial peer review double-blind process, 32 papers were accepted for publication and presentation, in which 12 were from field of structural engineering, 10 from construction management, 4 from transportation engineering, 3 from geotechnical, and 4 from water resources engineering. In addition to these technical papers, for the very first time in ICEC, there were invited talks from industry in each and every session. The contribution of these technical papers were not only from engineering universities across Pakistan, but foreign universities as well. With that, I would like to thank IEP and NED University for providing me this opportunity to be part of this conference. Thank you very much.
Right, I would now invite Engineer Sohail Bashir for his remarks.
Bismillah ar-Rahman ar-Rahim. Engineer Siddiq Isa, President, Association of Consulting Engineers Pakistan, and Chief Guest for this closing session, Professor Roger Ballum, Professor Emeritus, University of Colorado, USA, just left a little while ago because he has to catch up some program, and then this evening, tonight, he'll be leaving. Again, my very good friend, Professor Dr. Sharoz Lodi, Vice Chancellor, NED University of Engineering and Technology, a very good supporter and collaborator for this whole conference. Of course, very dear and near friend, Mr. Randolph Lagenbach, conservation tech and keynote speaker. And probably in the next 4 days, he is going to photograph all the old buildings of Karachi, and he will come up with a presentation like this very soon. Professor Said Kinai from Algeria, Professor Engineer Yusuf Mihani from Algeria, Dr. Mir Shabbar Ali, Dean, NED University of Engineering and Technology, Dr. Sadur Rahman, Chairman, Civil Engineering Department, NED University, Engineer Farah Adil, past Chairman IEP, my dear good friend, Engineer Masood Ahmed Khan Sahab, Chairman IEP Lahore Center, Mr. Raza Shah, UNESCO Islamabad, Ms. Reena Rafliana, International Center for Interdisciplinary and Advanced Research from Indonesia, Dr. Abdul Jabbar Sangi, Mr. Engineer Shamsun Farid, Engineer Farooq Arabi, and all ladies and gentlemen, Assalamu alaikum, and a very good afternoon. Well, as a chairman of the Institution of Engineers Pakistan Karachi Center, I thank all of you for giving your time in this 2 days international conference on civil engineering, which is the 10th one. And for the last almost 5 years, it is on a yearly basis without any break. And all credit goes to the dynamic leadership of Dr. Saroj and his team of NED University and our associate partners, which includes 2 universities from Balochistan, Balochistan University of Information Technology, Butmis, where another very good friend, Ahmed Farooq Bazai, is the Vice Chancellor. And from this year, we have also taken on board another university from Balochistan University of Engineering and Technology, Khuzdar, again, a very good friend, Dr. Ihsanullah Kakar is the Vice Chancellor, plus the Sir Syed University of Engineering and Technology and DHS Sufa University, which is going to start the civil engineering program from this year. So they all are on board in this conference. We got very good, excellent presentations during this conference, and another noticeable point of this conference was the invited speakers. Previously, our conferences were tilted more towards academic and less towards the real-time experience sharing. So from this year, we already did that in January in the electrical engineering conference, and now we repeated this story in civil engineering conference, that in each and every technical session, we invited speakers from the industry to share their experiences. And I'm delighted to bring on record that this has created a huge impact. Though all those things which were in the consultant's office or in the contractor's office in their backyards, it has now been shown as a showcase to the attendees of this conference. And I think I am delighted to say that this was a very good experience, and inshallah we'll continue this. In one of the yesterday's technical session, we gave the floor on a very heated issue regarding the K4. And the speaker gave us the actual situation, what is happening in K4. And probably at the end of the technical session, I have commented that this needs to give big time, and probably I will arrange a forum on K4 to invite everybody, because as the presentation was there, we all who have attended the presentation thought that something is going very big wrong, and it's time to highlight the issues, and not without blaming, because blaming is a simple game. What I look forward is that whatever has been done, how to improve upon to deliver the project. That should be the theme. So with that theme, inshallah, soon we will take up this K4 matter. Plus, we also took up the issues of the bus transit system, the green line, blue line, orange line. Again, there was a very good presentation. Again, what are the issues related to that was highlighted. And probably the Institution of Engineers Pakistan Karachi Center looks forward to develop policy documentation for the Sindh government, for the federal government. We have a pool of expertise of our engineers, and we would like to make use of all these expertise so that something positive could be contributed towards society. And in that area, I am pleased to also let you know all this, that with the help of UNSPIRE Indonesia, UN Inspire Pakistan, which was established 3 days back, and with the help of UNESCO Islamabad. Just this morning, we had a very excellent international workshop on role of youth and young professionals in science, technology, and innovation for disaster risk reduction. So again, for this particular effort, I am thankful to Mr. Raza Shah from UNESCO Islamabad, Riana Rafiana from International Center for Interdisciplinary and Advanced Research, Indonesia. Of course, the person behind in the issues related to UN Inspire, Shoaib, and all of those young graduates, young engineers, young professions, because it is an interdisciplinary approach. So we have not only engineers, but also from other fields. They all are here, and I'm really happy to say that this workshop will be the stepping stone to do a lot of things in the disaster risk reduction. And as chairman of the IEP Karachi Center, I have already given my promise that we will do everything and anything for them to develop this culture of disaster risk reduction in our younger generation, because they are our future. So with these words, I thank again all of you for your presence here, and look forward to see you again and again in our activities. And I'll request all of you to please take active participation in the issues of IEP, because IEP means dissemination of knowledge in every form to everybody. So let's do it. Thank you very much.
Thank you very much, Suhail Saab. Now I would like to invite the chief guest for today, Engineer M. Siddiq Isa Saab, President, Association of Consulting Engineers of Pakistan. Isa Saab, please.
Bismillah ar-Rahman ar-Rahim. Assalamu alaikum and very good afternoon. After listening to Bashir, I think he's quite committed to carry on the activity of engineering from various aspects. Professor Lodi and I give a lot of appreciation to Institution of Engineer Pakistan and NAD University of Technology for arranging this conference. I won't take my time. I know it's lunch time and you must be feeling hungry. So do I. But few words. A lot has been presented here, especially regarding the technical side and research side. At the moment, what I feel that Pakistan is undergoing is award of works, carrying out of the works, things like that. And unfortunately, for past half century, we have not been able to achieve the level which we should have. Procurement of services and construction is a very important part for any project. Though few years back, the government has come up with PEPRA, that's a rule for the procurement of goods. But I feel they're either due to the officers of the concerned departments are not very knowledge of procurement, they most probably make decisions which becomes controversial. So, first of all, I will request my friends here in IB to arrange a very full-fledged program for all the departments to teach them what this procurement rules and regulations are, so that unintentional mistakes do not occur. Second is the related problem again with the procurement, and that is overriding time and the cost. These two things again in Pakistan is eating up the credibility of the government department and the credibility of the professionals and the contractors. I think we have to take a very serious view and discuss as various platforms these issues regarding procurement. At the moment, you must be also hearing on electronic media and there's a debate going on about the award of work for the dam. If we are fully aware of procurement rules and regulations, we will not waste our energy on unnecessarily going against or going in favor of, but the work should be awarded according to the already framed procurement rules. There are two of these. One is on federal level and another is at the provincial level. Again, there are problems for the officers who carry out this work because they have to look on the two documents. I don't know why it has been done, but it is there. And so far, if you are practicing in Sindh, you have to go according to the procurement policy of the Sindh government, which is a different rules than federally regulated. I'm very impressed by Rudolph's paper, and all civil and structural engineers sitting here. 90% of the projects in Karachi and other parts of Pakistan is being designed with block masonry partitions. Because in Pakistan, we don't have still tuned to the idea of using soft partitions, which is so prevailing in other countries. I myself, a structural consultant, I feel the use of concrete partitions itself a burden on the building, because this increases the weight of the building and the forces, earthquake forces, are in proportion to the load of the building. The more load we have, the more earthquake forces, and that means more design problems and the cost, increase in cost. This is high time that our engineers and architect people should try to convince the owners that let's go on to the soft partition, which will not only reduce the weight, but the risk of earthquake collapse of buildings. Especially many of the projects, if you will visit, you will see the ground floor, there are no partitions. And this is Rudolph also presented in his paper. The reason is either there are business activity on the ground floor or it is a reserve for the car parking. The upper floor got masonry walls. And the recent practice in Pakistan, which I don't subscribe, but it is going on, that all the block masonry walls are integrated with the structure, making something like shear walls on the top floors and a very soft story on the ground floor, which can cause the collapse of the building. I fully subscribe to Rob's idea of using mortar. The strength of the mortar should be less than the strength of the masonry itself. I don't know, however, that if there are a few cracks because of that and not because of structural cracks, there will be hue and cry. So best thing to do is to have a soft partition of gypsum or other material which are lightweight. I thank you again for inviting me to have an interaction with my fellow engineers and Mr. Geologist who has already gone. I should have told him that no problem, engineers and geologists are, if they are not brothers, they are at least half brothers. So with these comments, I once again thank you all the officers of the IEP and NAD University for arranging such a good conference, which will be very beneficial to all of you. Thank you. Thank you.
Thank you very much, Siddiq Issa Sahab. In his first part of address, he highlighted a very important aspect related to procurement and the contract management. So I would like to add that at NAD University, we have already introduced construction contract management as a course in the undergraduate program as well. There are a couple of modules which are covering procurement in details. And then very soon, we are going to start a master's program called Masters of Engineering Law. That particular program specifically addresses all the legal aspects, including construction, contract management, procurement. So very soon that program would be launched. Every year, as part of the International Civil Engineering Conference, the papers which are presented are actually evaluated by the session chairs. This year we had 9 technical sessions where 32 papers were presented, and based on the detailed evaluation of those papers, one best paper is selected and Chairman IEP's medal is awarded. So this year, based on the evaluation by the session chairs, the title of the paper which is awarded Chairman's medal is Evaluating Water Quality of Mali River for Detrimental Effects on Vegetables and Groundwater. The authors were Sania Siddiqui, Komal Abdullah, Sana Wajid, Roha Tariq, Nageen Yusuf, Shanza Sattar, and Professor Dr. Imran Ahmed. So a big round of applause for the winning paper. If we have Sania or Komal over here, no, I would request Ms. Saima from Department of Civil Engineering to kindly come forward and receive the medal on their behalf. Engineer Suhail Bashir and Siddiq Issa Saab are requested to, Siddiq Saab, kindly if you can join. Now I would like to invite Professor Dr. Mir Shabar Ali for his concluding remarks.
Bismillahirrahmanirrahim. International dignitaries, academics, practitioners, my dear students, and all IEP and NED University members, Assalamu alaikum and very good afternoon. I'm really honored to be part of this closing session, which I feel is as good, have got the attendance as its inaugural session. And I have witnessed a very good conference for the 2 days. Sometime I could not get a place to sit in the technical session as well. So the beauty of this conference is that, as Suhail Bashir has already mentioned, that this time we invited the practitioners, the industry to be part of it. And I'm happy to see that this kind of collaboration will be, inshallah, growing. As being honored to be the part of NED University as well as IEP at the same time, being the member of the local council, I congratulate the whole team. And I see that, especially I would mention the inaugural session as well as this closing session was addressed by 2 very highly eminent academics and professionals. So that both of them has actually given us lot of opportunities to think about. And I think there is a lot of work can be done in the next year, so that inshallah in the next conference, when we come back, we will be getting fruits of that, especially whatever Dr. Naveed Anwar told in the morning yesterday, and what all the Randolph has told us today. They give us a lot of opportunity to think about. Second thing, I will also admit that by doing all that, we have actually raised our mark, and now it has become our challenge to, inshallah, to be on the same mark and maybe higher than in the next time. Thank you very much.
Thank you very much, sir. Now we have time for presentation of mementos to distinguished guests and the delegates and the organizing committee members. So I would like to invite Siddiq Isa Saab and Sohail Bashir Saab to kindly come up here for presentation of mementos. I would also request Farooq Arbi Saab to kindly join them. So memento to be presented to our keynote speaker for today, Mr. Randolph. I would now request Mr. Engineer Sohail Bashir to present memento to Mr. Siddiq Isa Saab. Professor Dr. Mir Shabar Ali. Professor Dr. Asadur Rahman, Chairman, Department of Civil Engineering. Conference Secretary, Dr. Shamsoon Farid. Now we have members of organizing committee. Dr. Syed Salman Mubin. Dr. Aslam Fakir Muhammad. Engineer Fatma Khalid. Engineer Waleed Ahmed Khan. Engineer Shoaib Ahmed. Engineer SM Noman. Engineer Sajjad Ali. Noman and Sajjad both. Engineer Fawad Masood. Noman. Engineer Fawad Masood. Dr. Tahmeena Ayub. Engineer Wajia Mahmood. Dr. Saria Bukhari. Engineer Sadia Muin. Engineer Saima Khan. Engineer Faiza Saeed. Now our collaborating partners. Engineer Dr. Azmatullah from Butins, Quetta. Engineers Syed Fazal Abbas from DHA Sufa. Fazal Abbas Bakri Sahab from DHA Sufa. Dr. M. Farooq Shahab from DHA Sufa. Right, now we have presentations for the international workshop, U-Inspire workshop on disaster risk reduction. I would like to invite to receive her memento, Ms. Irina Rafliana. Mr. Hilman Arioji. Mr. Hilman Arioji. Mr. Raza Shah. From UNESCO Islamabad. Ms. Ghazala Naeem. Left. Mr. Shoaib Ahmed. We have more than 30 participants in the U-Inspire workshop. Now the certificates would be awarded to the participants. Muntaha Atiq. Please, all the workshop participants, if you can come forward. Laiba Salim. Laiba Salim. Hamna Azam. Sheldon. Hassan Beg. Maria Khan, Hira Nadir, Syed Ehsan Abbas, Minha Abbasi, Mueed Mujib Jilani, Engineer Afaq Ali Siddiqui, Engineer M. Sharik Khan, Engineer Talha Khalid Dar, Engineer Ali Javed, Engineer Arham Asif Mannan, Dr. Fazal Abbas Bakri, Engineer Faiza Saeed, Engineer Nimra Saeed, Engineer Mariam Anwar, Engineer Aisha Feroz, Engineer Zarlasht Basharat, Engineer Afaq Ali Siddiqui, Engineer Hiba Nuzat, Engineer Rabia Binte Suhail, Laiba Ayub, Laiba Ayub, Murtaza, Mr. Rehan, Syed Abdullah Shah, Engineer Nabil Kalu, बस मेरी शील्ड है अब आ जाइए
Thank you. I think we need to give a big applause to Dr. Abdul Jabbar Sanghi for the very well done. Siddiqui sir, please. He was the co-convener of this whole conference. Before we conclude this session, I'll request Mr. Raza Shah to share some thoughts about the workshop, and then also I'll request Arena to give a small sharing of your experiences of the conference. First, Mr. Raza Shah from UNESCO.
Thank you, Sohail Saab, for giving me opportunity to share about UInspire. UInspire is a platform for youth and young professionals to utilize science, engineering, technology, and innovation for DRR, disaster risk reduction. The idea started a few years back when UNESCO was working to promote science, engineering, technology, and innovation. And last year in Jakarta, we had a regional workshop where 52 participants from 30 countries, all young professionals, participated. And that's where UInspire Indonesia was launched officially. And Mr. Shoaib from NED University participated from Pakistan. And with all the excitement and lessons learned from Indonesia, he came back and launched UInspire here in Pakistan on 21st of February here. So, and today, we had its first workshop, and we invited 30 young professionals, students from all walks of life. They were not only engineers, because when we are talking about disaster risk reduction, it is a very complex thing. So that's where we want to give awareness about the whole program and this platform with those participants. And now we have a roadmap with us. We have a way forward with us after this workshop, and soon we will share that roadmap with all the relevant stakeholders and partners in the country. It is an open platform with loose bindings. Anyone can participate. It's not only youth. All senior officials and engineers and government officials can participate in it as well. It is open for all the ideas. So basically, this platform is a knowledge sharing, ideas sharing, experiences and expertise sharing platform. It is to raise awareness, basically raise awareness about how science, engineering, technology, and innovation can play an important role for disaster risk reduction. Thank you.
Thank you, Mr. Raza. I'll now request, this is out of box, whatever now we are doing. So now I request Arena, please share your experiences about the workshop.
Assalamu alaikum. Thank you very much, Dr. Shoaib, Mr. Rajasan, all of my colleagues, friends, and mentors in this room. I am so honored once again to be able to be standing up here. I was asked by UNESCO to come to Pakistan, and I question not. I just asked my husband, will you allow me to fly to Pakistan? And he said yes. And I'm so happy to, at the end, be able to be here. I share the stories about visits, about interactions with all of the wonderful people here, to my son and to my husband at home every night. And it's such a memorable experience for me. That's a personal impression about Pakistan, and please do kindly accept if I and Rio come again to Pakistan. We would really love to come again, work together again with all of you. The world is now facing much more complex risk. It's not as simple as we thought it was in decades before, and that is what is challenging all of the youth and young generations today. The population, the culture, the economics, the technology advancement, including the vulnerability of people, but also the strength of the communities, women, children. It's really in the hand of the young generation to think about ideas out of the box or break the box, the silos, the disciplines. We're probably now in the conference of civil engineering, but definitely need lots of insights from the economics, from sociology, anthropology, you name it, communication. That is the difference between today's generation and the previous one. We collaborate more closely. So I am here to pledge my full support as the member of the Science and Technology Advisory Group to the United Nations International Strategy for Disaster Risk Reduction, UNISDR, and also as my affiliation, Indonesian Institute of Sciences, I would look forward to work more closely with Pakistan in different wide area of sciences and its application. I would like to see in the future, if we are exposed to hazard, we will all be grateful because nobody is in danger and nobody is in harm, because all of us had already worked hard from today to now on, inshallah. Again, thank you very much. Assalamualaikum warahmatullahi wabarakatuh.
Before we conclude today's session, I would like to request in the end Engineer M. Farooq Arbi for his vote of thanks.
Bismillahirrahmanirrahim. Alhamdulillahi Rabbil Alameen. Wassalatu wassalamu ala Rasulil Kareem. Engineer M. Siddiq Isa Sahab, President, Association of Consulting Engineers of Pakistan, our chief guest today, all the foreign dignitaries, national, our guests from Lahore, Islamabad, Assalamu alaikum. It is my great privilege to extend a vote of thanks on the occasion of this 10th International Civil Engineering Conference being jointly organized by the Institution of Engineers Karachi Center and NED University of Engineering and Technology. We are extremely grateful to the chief guest, Engineer M. Siddiq Isa, who accepted our invitation to grace the occasion as chief guest. Sir, we thank you for sparing your very valuable time on this closing session of the 10th International Civil Engineering Conference. As you all know, the organization of such events are generally the result of close cooperation among several institutions and individuals. It is my great pleasure to express on the behalf of local center, IEP Karachi Center and organization, and on my behalf and on behalf of the local council, I deeply appreciate for the support and encouragement provided by such individuals and institutions. This event is a collaborative effort of the Asian Civil Engineering Coordinating Council, Federation of Engineering Institutions of Islamic Countries, Federation of Engineering Institutions of South and Central Asia, Association of Consulting Engineers of Pakistan, Balochistan University of Information Technology, Engineering and Management Science, Quetta, Balochistan, University of Engineering and Technology, Kuzar, Sir Syed University of Engineering and Technology, Karachi, and DHS Sufai University. My regards and thanks to Engineer Suhail Bashir, Chairman IEP Karachi Center, who always a source of motivation of such events of institution. We started working on this conference last year as Vice Chairman Civil under the guidance of Engineer Professor Dr. S.F.A. Rafiqi, who was Chairman at that time. I take this opportunity to extend our most sincere thanks to all our guests, invitees who have come from different destinations for their support and cooperation, and this all on this day, that Sunday. Many of the experts, having vast experience in the field, have been kind enough to accept our request and share their experiences as invited speakers from different technical sessions during the conference. The authors from different parts of country presented their case studies also deserve compliments. The international resource persons have brought here with them and shared with us their knowledge and experience. You have guided us in the right direction, and we appreciate that. We understand that you have taken time out of your very important schedules to contribute to this conference, and some of you have even traveled at a very short notice. Thank you for your valuable contribution. My thanks to Engineer Sarosh Hashmat Rodri, Vice Chancellor, NED University of Engineering and Technology, and the convener of this conference, and Engineer Dr. Abdul Jabbar Sangi, co-convener of this conference. Their suggestions, timely advices, and personal efforts have made this conference a great success. My thanks to all of you who have traveled from various parts of the country to grace this occasion have become a great source of encouragement for us. My sincere thanks to all the authors who presented their valuable technical papers. My sincere thanks to all the authors whose paper could not be included in the conference due to limitation of time. My sincere thanks to our foreign delegates who presented their research papers, particularly Dr. Naveed Anwar for presenting his keynote address yesterday in the inaugural session, and Engineer Mr. Reynold Legenbeck for presenting his keynote address in this closing ceremony. My thanks to all the organizations who have supported to make this event a success. My special thanks to media and press for supporting the events. My sincere thanks to members of the organizing committee for their efforts in organizing this conference. It has been our pleasure to thank all the participants of the conference. The participants were very enthusiastic. We have been fortunate to have some of the eminent persons from academia and industry working in the area of civil engineering. I am sure that the participants must have benefited by attending this conference. I take this opportunity to thank all the reviewers and technical committee members for providing their valuable comments in time and help toward the improvement of quality of papers presented in the conference. We also thank all the session chairs for chairing the technical sessions of the conference. I know I'm taking long. And I appreciate that you appreciate. An event of this dimension cannot happen overnight. The wheels started rolling months in advance. It requires meticulous planning and execution and an eye for details. We have been fortunate enough to be backed by a team of very motivated and dedicated colleagues who know their job and are result-oriented. I cannot thank everyone enough for the involvement they have shown and the willingness they have expressed to take on the completion of the task beyond their comfort zone. And finally, my thanks to members of our staff, office staff, who have worked really very hard and for long hours and have contributed great towards the success of their conference, and they really deserve a round of applause. In the end, my most sincere and deep-hearted thanks and gratitude to Almighty Allah who gave us the courage and strength to hold this function with full justice. Thank you very much. Allah Hafiz. Pakistan Zindabad. The lunch is ready. Please proceed to the dining room.
Thank you very much.
All the participants of the workshop, they are requested to please join for a group photograph. And secondly, all the speakers and foreign delegates first, please come forward for the group photograph. And followed by this, the workshop people.